We've been graphing arcs on the Argand diagram of the complex plane, and we've come to this particular example which we did in class, but the way that I graphed it and obtained the Cartesian equation relied on a lot of visual thinking and geometric reasoning. Now, a lot of people feel uncomfortable with that because it feels a bit like guesswork and that you have to do a fair bit of it through insight, and if someone hadn't shown you how to do that, you wouldn't be sure how to do it. So I'm going to show you an alternative method now, which is to rely on a lot more algebra. I will point out, you will never escape being able to think about these geometrically, because if you're graphing something, you're going to be drawing, you're going to be on the complex plane. But what I'm going to show you here may feel like it puts you a bit more at ease in terms of there is a less hand-wavy way to go about it. Relying on the algebra, you can find out the points precisely. However, I do want to strenuously point out, this is not an ideal way to go about it. You're going to see it's very long and therefore error prone, and so this is not my recommended method, but it's good to know multiple ways to get to an answer, and it's also very assuring when you can take different paths and still arrive at the same solution. So hold on to your hats, let's have a go together. Graph arg of z minus 1 on z plus 1 equals pi on 4 on an Argand diagram. All right, so the first thing that we notice is this is going to be an arc of some kind, because having this comparison of angles here, if we had pi on 2, it'd be a semicircle, but it's pi on 4, so it's an acute angle, it's an acute angle, and that gives us a major arc. To remind you of why that is, you just think about how arcs form angles within circles. If you have an obtuse angle, a wide angle like this, that necessarily makes the arc that you're standing on very long, and so the arc that you actually form up above is going to be very small. And by contrast, when you've got an angle that's acute, like the one we have in our question, that creates a large arc above you, and that's the one that we draw, and a small arc beneath you, which is kind of the one that is excluded from the actual subset of the complex plane. So therefore, I already know that I'm going to get a major arc from this, so let's just note that down, major arc. And then I also notice that I've got these two reference points here. Now, to make it a little bit clearer what the reference points are, I'm going to do a couple of things. So firstly, I'm going to break apart, remember we're doing this algebraically, I'm going to break apart this big argument into two arguments. The argument of a quotient, when you're dividing one complex number by the other, is you subtract the arguments of each of the individual complex numbers. So therefore, I will subtract arg of z plus 1. That equals pi on 4, and then I note it's really, arg of z minus something. Even though this is written as a plus, I should write it as a minus to indicate the actual reference point that I'm referring to. So this one's already fine, I don't need to change it, but then this one here, it should be z take away negative 1. So these are our two reference points here, 1 and negative 1, and importantly I note the direction. So 1 is going to be my start point, negative 1 is going to be my end point, and I'm going to go anti-clockwise around the arc to do this because we measure all arguments, angles on the complex plane, in an anti-clockwise direction. Okay, now at this point, you really cannot escape doing at least a rough sketch so that you guide what future algebraic working you do, because otherwise there's a whole series of things that you could do here that might be helpful or unhelpful depending on what kind of shape that you've got. So let's have a rough sketch here. You can see I know that I'm going from 1 to negative 1. So if I just pop some very rough points here, 1 and negative 1, and I've drawn the top half of the complex plane because I know going anti-clockwise from 1 to negative 1 will send me in this direction here. So if I were going in the other direction, from negative 1 to 1, then anti-clockwise would take me onto the bottom half of the complex plane. So you've got to think carefully about where your points are and what direction you're going in before you even draw anything. Okay, now what I'm going to do is I'm just going to draw a very rough, whoopsie daisy, a very rough arc around there. It's pretty terrible, but all I need is a rough sense of where's this thing going so I can start to work out some points. Now, you can see that it's no need to find x-intercepts because I already have them, right? The 2 points that have been provided are both on the real axis, so I don't need to find those. But I immediately notice that there's this spot up here, which is obviously, like whenever we graph something, we want to know what the intercepts are. So this is an imaginary intercept. It's on a y-intercept, which is on the imaginary axis. So how do I find an imaginary intercept? Well, if I'm finding a y-intercept, then what I usually do is I let x equal 0. Now that is the way that I go about it, but you can see when you have a look at this question, it is not set up at all to find, to let x equal 0, because there aren't even any x's in the equation. So we need to introduce them. To get toward a Cartesian equation, which is in x and y's, and to solve for a point which has an x and a y component, what I need to do is I need to say, well, let's let z equal x plus iy. Doing that, let's just substitute in. I get arg of x plus iy minus 1. So there's the z minus 1, which you can see in the previous line. And then I take away arg of x plus iy. I'm going to put this back to being plus 1. The reason why I put it as minus -1 is to make it clearer what the reference points are. But I know where they are now, so I can write it in this simpler form. Okay, so this is equal to pi on 4. That's progress. At least I have x's and y's now, so that when I want to find the imaginary intercept, which I should write down, I can just substitute in that there's no real component, or that the real component is 0, is a better way to say it. So to find the imaginary intercept, what I'm going to do is I'm going to let x equal 0. So what does that give me? I'm going to have arg of iy minus 1 minus arg of iy plus 1. Okay, so what have I done here? You can see my x's have just kind of vanished away because I've substituted 0 into them. So this line looks weird, but why did I say 0 on the end there? It's pi on 4. This looks weird, but it's true, and apparently if I solve this, then I'm going to get some y values which will represent this y-intercept. So how do I go about that?